Today we're going to look at cooperative games with transferable utility. We're going to talk today mostly about one example, but this will apply in general in the exact same way that it applies to our example here. So say we have this two-player general sum game with payoff by matrix given by the one shown here. Player 1 plays rows, and player 2 plays columns. The payout is given in these four pairs of numbers, the first one for player 1 and the second one for player 2. I've drawn the feasible sets. We talked about those in the last lectures. The feasible set where there's no transferable utility consists of the convex hull of those points on a graph here. The horizontal axis represents the payout to player 1, the vertical axis to player 2. We plot these points that represent the payouts, and those represent the pure strategy options, those 4 points. And if we look at mixed probability combinations of those 4, we get the entire convex hull of those 4 points. Now, with transferable utility, that means a side payment can be made. So once some sort of combination, probability combination of these 4 outcomes is chosen by the 2 players, they can then just have a side payment. We'll represent that as the number S, which will represent the payment from player 2 to player 1. So a positive number S represents this payout from player 2 to player 1. What does that do to an option? Well, here, if they've decided to have player 1 play row 1 and player 2 play column 2 and end up at this position 4-2, that's right here, a side payment S would move us to a different point here, 4 plus S, 2 minus S. It's a payout from player 2 to player 1. So if S is positive, we move down here. If S is negative, we move up here. We could move anywhere along this line here, which is a line that represents the sum of the variables. If I call X the first position and Y the second position, it's just the graph of X plus Y equals 6. The sum of the 2 payouts is 6, but we can end anywhere up on that line. And we can do the same thing with side payments from any point in the non-transferable utility, the NTU feasible set. So we can imagine that a line here at the same 45-degree angle with respect to the axes. We make that from any point. And what we actually get is this entire strip here. Let me make a different color here. This entire strip represents the feasible set when transferable utility is allowed. At this point, I want to make a definition that we haven't had before. We say that a choice for payout, and this would include with a side payment as well, a choice of payout is called Pareto optimal if it's one for which no player can be made better off without harming the other player. Let's see an example here. If they decided to choose some mixed strategy combination of the different rows and columns that ended up here, that would be far from Pareto optimal. You can make player 1 much better off just by moving over to here without making player 2 worse off at all. Or you can make both players better off by moving up to here. This idea of Pareto optimal is important because it should be clear that if it's a cooperative game and there's transferable utility, one would never want to pick an outcome that isn't Pareto optimal. In other words, one would always want the Pareto optimal outcome, because if it's not, just do whatever's necessary to move to a situation where one player is better off without hurting the other, or where both players are better off. So here again, I've drawn the feasible set. I haven't drawn the entire feasible set, but I've drawn the convex hull of the 4 points. Remember, inside that the convex hull here represents the feasible set in the non-transferable utility case. And I've drawn this line here at the point 4, 2. because it should be clear that any Pareto optimal outcome, and remember we said we can definitely move to a Pareto optimal outcome. We would never want to stay at an outcome that's not Pareto optimal. A Pareto optimal outcome is the one which is you get by moving up and to the right. Well, if you remember the entire feasible set for this transferable utility game, it consists of this strip. And to get a Pareto optimal outcome, we move up and to the right. We'd have to end up on this line here over to the right, the line where x plus y equals 6, if x and y are the payouts to player 1 and player 2. So we want to end up somewhere on this line in the upper right. The question is where? Well, we can achieve 1 point on that line just by playing the pure strategy 4-2. Remember, that's player 1 chooses row 1, player 2 chooses column 2, and that gives us a total payout of 6. That's what the book uses the notation sigma for. Sigma is 6. That's the maximum total payout. But then if there's a side payment we can get anywhere else on this line, the question is, what agreement might be fair to both players? We saw even very quickly in the last lecture that player 2 probably feels a bit ripped off if we get this outcome. Remember, player 2 would get a payout of 3 at this point. That's better for player 2 than down here. Of course, it's substantially worse for player 1. So player 2 might just say, I don't want to do that. I could play here and do better. Well, that brings up other problems. The question is, what can both players do together to arrive at a payout that seems fair to both players, that both players would agree that they're satisfied with? Well, this idea that a player is dissatisfied because a player could make a threat to just violate to not agree to this position, which has the maximum total payout, and instead play one that's more profitable for that player. That idea of a threat we can formalize very simply. We just ask, what's the best that each player can do all by him or herself without even considering what the other player does? Well, how would they do that? So we'll talk about how in just a second. So let's just talk about the notation first. Say each player decides on a threat. This will be some probability vector P for player 1 and some probability Q for player 2. Remember, P in this case would just be a probability vector, say P1, P2, where P1 is the probability for player 1 to play row 1, P2 for row 2, and Q will equal Q1, Q2 with probabilities for column 1 and column 2. Let's just say they decide on those as threats. We're going to call the point D the threat point or disagreement point. What is this point D? That's the point in this feasible set, so it should be in the convex hull of these pure strategy options, which represents the payout player 1 can receive if player 1 plays probability vector P and player 2 plays strategy with probability vector Q, and D2 is the payout for player 2. So this point D is the point here, D1, D2. Well, can we compute D1 and D2? Well, D1, of course, is just the payout for player 1 with these strategy choices. That's just P transpose AQ, where here A is player 1's matrix. In other words, the matrix for player 1's game. What is that matrix for player 1's game? Well, in this situation, that's just the matrix 1, 4, 0, 2. And B is the matrix for player 2's game. And for this particular example, you remember here these points. B is the matrix 3, 2, 0, 3. So we compute D1 and D2, and we get this threat point or disagreement point. Now, how do we move from that threat point to find a fair side payment that lets both be much better off than they would be at that threat point? Well, here I put the threat point again, just some point in this convex hull of the pure strategy choices. Since we call it a threat point because player 1 can guarantee an outcome of at least D1 without any cooperation from player 2. So if I put a vertical line here from this threat point, player 1 would never accept anything to the left of that, because even with no agreement whatsoever, player 1 can guarantee at least D1. Similarly, if I put a horizontal line, remember player 1 is on the horizontal, 2 is on the vertical. If I put a horizontal line here, player 2 would never accept any number below D2, below this line, because player 2 can guarantee at least D2 all by himself without any cooperation from player 1. Now, let's mark some of these things on the graph. Remember, we had sigma equals 6. That's the total payout, the maximum total payout among the pure strategy choices. And then what is the location of this point? Well, the sum of the two entries has to be sigma, so this entry has to be sigma, let's see, I'll say the x coordinate has to match the d1, so it'll be d1, and then it'll be sigma minus d1. This point here will have vertical component d2, and so the horizontal component will be sigma minus d2. I know that's a little bit sloppy, but let me fix it. So we can consider these points to be kind of the extreme points along this feasible line. I call this the feasible line because every point on this line has the same maximum total payout of 6, but these are places at least which might be considered. The players won't consider anything up here because then player 1 would be worse off than at this threat level. We won't consider points down here because then player 2 would be worse off than at the threat level. So somehow we would like the players to agree to get the maximum total payout, and then there might be some transfer, a side payment that gets them to some other point along this line. Here's a natural way to pick a value for a side payment. Look at this line that makes a 45-degree angle with these other, the horizontal and the vertical, and look where that intersects the feasible line. We're going to call that point phi. I claim at this point, both players, if they decide to move towards this point, both players will receive the same amount above the amount they could achieve all alone. And that's one which I think both players could agree is reasonably fair. I'm not saying that the agreement that they both necessarily will, but there's a reasonable argument for both players to say, if we pick a side payment, we make an agreement to get the maximum total and then pick a side payment to move to this point phi, then we each get the same amount above what we could achieve all by ourselves. In other words, the advantage from making the agreement is kind of equally divided among the two players. What is the location of this point phi? Well, it's clearly halfway in the middle between these 2 points, d1 and sigma minus d1, and sigma minus d2 comma d2, so we can easily compute the coordinates of this point. It's just in the x-coordinate, the average, which would be sigma minus d2 plus d1 over 2, and in the y-coordinate, the average of these second coordinates, which is sigma minus d1 plus d2 over 2. And then here's another way to write that, just doing some trivial algebra. We have sigma plus this quantity D1 minus D2 all over 2, and sigma minus this quantity D1 minus D2 over 2. Now, this is what they might agree to once they've chosen that threat point. The question we have to ask ourselves now is, how do they choose that threat point? Because there are lots of different threat points that could be chosen. Any mixed strategy that player 1 and player 2 decide would represent something that each player can achieve all by themselves, so that gives us lots of different threat points. Well, player 1 would like to choose a threat point that makes the x-coordinate, the first coordinate here, the biggest. And player 2 would like to choose a threat point that makes this second coordinate the biggest. Well, to make the first coordinate biggest, we want D1 minus D2 to be largest. So player 1 would like to maximize, that's what I have here, D1 minus D2. And remember, D1 is just this return for player 1 with strategy choices P and Q for the players 1 and 2. And D2 is this P transpose B Q, where again P and Q are these strategies for player 1 and player Q. Player 1 wants to maximize this, while at the same time player 2 wants to maximize this quantity, which is the same as minimizing D1 minus D2. So they both are looking at this one special quantity, and in order to pick the correct threat point, player 1 would like to make that best for player 1, which is to maximize this quantity. That will make the end result furthest to the right, the end result phi here furthest to the right. And player 2 would like to minimize this, which would make the end result highest, or furthest up. Well, how do we have the two players figure out how to maximize this quantity for player 1 and minimize this quantity for player 2? Well, that's something we actually looked at in the earlier part of the book. That amounts just to solving this particular game, A minus B, if we think of A minus B as a two-player zero-sum game. Remember, solving the game involved finding these strategies, P and Q, which for player 1 would guarantee at least this quantity, D1 minus D2, and for player 2 would be guaranteeing at most that. Player 1 would be maximizing this quantity, while at the same time player 2 would be minimizing it, and they would arrive at a single value and optimal strategies that each guarantee them that particular amount. So let's go back to our example. For this game, the matrices A and B, which we've already written down, are these. A is this matrix, B is that matrix. We now look at something totally different, this new game, A minus B, that we haven't looked at before. And then we solve it as if it were a two-player zero-sum game. And since it's a 2x2 matrix for a two-player zero-sum game, and you can see very quickly there's no saddle point, the optimal strategies will be equalizing strategies. The value of the game can be computed easily. The determinant, which is 2 minus 0 over negative 2 minus 2 plus negative 1 minus 0, easily computed to be negative 2/5. And you can see very quickly that the optimal strategies are P is 1/5, 4/5, and Q is 3/5, 2/5. Check yourself in your head that if player 1 plays row 1 with probability 1/5 and row 2 with probability 4/5, that whatever player 2 does, whether it's column 1 or column 2, the expected return is exactly negative 2/5. The same thing would be true for player 2 if player 2 plays column 1 with probability 3/5 and column 2 with probability 2/5. Whatever player 1 does, the expected return will be, again, negative 2/5. Well, we can now compute the threat levels, the disagreement levels. D1 for player 1, that's just the expected return for player 1 in this game when both players are playing these optimal strategies, in this game A minus B. And we can compute that as just P transpose AQ, which is, this is P transpose times the matrix A times Q. You can easily do that computation. I'll leave that to you. And you get the number 27/25. And the threat level for player 2, D2, is just P transpose BQ, which you can easily write this down. Here's the matrix B and here's P transposing Q, and you get 37/25. Notice here that D1 minus D2 is exactly -2/5. That was the value of this game, A minus B. The agreement point then is just going to be 3 minus 1/5. We get that by sigma, which is 6 minus 2/5 all over 2. That's the 3 minus 1/5, or 2 4/5 for player 1, and 3 plus 1/5. That's the sigma minus -2/5, or 6 plus 2/5 all over 2. That's 3 1/5. That's the payout for player 2. In the end, let's restate that clearly. In the end, the players should agree to play row 1 in column 2. They really want to agree to play this to get the maximum total payout, what we've been calling sigma, which is the 6. And they'll distribute that by making a side payment. How much is the side payment? Well, player 1 has to make a side payment of 6/5 to player 2. That will then reduce the amount player 1 gets from 4 down to 3 minus 1/5, which is 2 2/5. Player 2 gets 2 from choosing that point in the game, plus this side payment of 6/5 to get up to 3 1/5 for player 2's payment. Again, both players should be reasonably comfortable with this, since both players are getting the same amount more than they could get by themselves without any cooperation whatsoever.